All right, let's talk about cracking the code on some of those really tricky differential equations. You know, the ones that come in disguise. We're going to dive into some powerful substitution methods that can take a problem that looks totally impossible and turn it into something we can actually solve.
You know that feeling, right? You're staring at a differential equation and it just doesn't fit any of the neat little boxes you've learned. It's not separable, it's not linear, you feel like you've hit a wall. But trust me, it's probably not a dead end.
Here's the secret. A lot of those tough equations are just wearing a disguise. On the surface, they look super complex. But if you have the right tool, the right substitution, you can peel back that mask and find a much simpler equation underneath. So for the next few minutes, let's put on our detective hats.
So here's our game plan. We'll start by learning how to spot two of the most common disguises, homogeneous equations and Bernoulli equations. Then we'll get our hands on the special key that unlocks each one. And we'll wrap it all up with the final check that every good detective does to make sure our solution is legit.
Okay, first up, homogeneous equations. This is our first suspect. And the most important skill here is just learning how to spot it in a lineup.
So what is a homogeneous differential equation really? Well, the telltale sign is this. After you get it into the dy dx equals something form, that something on the right side can be written entirely as a function of the ratio y over x. That's the key. All the variables have to be bundled together in that one specific y over x package. Let's make this super clear. Look at the example on the left. The trick is to divide everything, every single term, top and bottom, by x. When you do that, what happens? You're left with an expression that only has that y over x ratio. See? That's our clue. That's a big yes. But now look at the one on the right. Try as you might, there is just no algebraic trick that will let you rewrite x cubed minus y cubed using only y over x. So that one's a no.
Okay, so you've spotted one in the wild. You've identified a homogeneous equation. Now how do we crack it? We need the key.
And this is it. This is the master key for every single homogeneous equation. We're going to make this substitution y equals v times x. Now, it's really important to remember that v here isn't a constant. It's a new variable that's a function of x. This one little move is going to completely change the game. Let's walk through the procedure. Step 1, you swap out every y with vx, but you also have to swap out the dy by dx. Using the product rule on y equals vx, the derivative becomes v plus x dv by dx. And here's where the magic happens. Because the original equation was a function of y over x, and since y equals vx, that means y over x is just v. So the whole right side of the equation just becomes a simple function of v. From there, it's just algebra. You shuffle things around until you get all the v terms on one side and all the x terms on the other. Bam, it's a separable equation. Now you can integrate, and for the final step, don't forget to substitute back v equals y over x to get your answer in terms of y and x. All right, one disguise cracked. Let's move on to our second case file, the Bernoulli equation. This one's a little different. It has a sneaky little twist. Okay, so a Bernoulli equation is a real trickster. It looks almost linear. See? You've got your dy dx, you've got a p of xy term. It all looks so familiar. But then over on the right, you've got this little troublemaker, q of x times y to the power of n. That one term, that y to the n, is what messes everything up and makes the equation nonlinear. But here's a pro tip. You don't always need a special tool for this. If the n value happens to be 0, well, y to the 0 is just 1. And hey, the equation is already linear. And if n is 1, you can just group the y terms together and solve it. So we only pull out our special Bernoulli substitution when n is something other than 0 or 1. So for all those other cases, when you've got a true Bernoulli equation on your hands, what's the plan? You guessed it, it's another clever substitution. And here is the exact key for this lock. The substitution is u equals y to the power of 1 minus n. And that n is the very same n from that troublemaker term in the original equation. This is the one to remember. It's tailor-made for this exact problem. So why do we do this? What's the point? It's all about transformation. We're not trying to solve for y directly. Instead, we use this substitution to translate the problem. We turn the complicated, non-linear Bernoulli equation into a nice, standard, linear equation in terms of u and x. And that's a type of problem we already know how to beat. The process is pretty methodical.
First, you just identify all the pieces from your equation, your p of x, your q of x, and that exponent n. Then you set up your substitution, u equals y 1 minus n. The next step is a little tricky. You have to find du dx, and that's going to take the chain rule. Once you have that, you plug everything back into the original equation. It'll look messy for a second, but then the dust will settle and you'll be left with a linear equation for u. You can solve that using an integrating factor, and then the final move, of course, is to substitute everything back so your final answer is for y.
Okay, so we've learned how to crack two different kinds of codes. We have our solutions. But hold on, we're not done just yet. A good detective always does one final check to make sure everything adds up. This part is absolutely crucial. Why is this so important? Because an answer isn't just a formula. It's a formula that works over a specific range, a specific domain. Think about all the algebra we just did. Along the way, did we divide by a variable? Almost certainly. And what's the number one rule of math? You can't divide by 0. That move creates a restriction that we have to account for.
So here's your final checklist. Go back and look at your work. Did you ever divide by x? If so, x can't be 0 in your solution. Did you divide by y? Then your solution can't cross the x-axis. And a classic one, if your final answer has a natural log in it, remember that the thing inside the log has to be strictly positive. Always, always state the valid interval where your solution lives.
And, that's really what this is all about. Learning these methods, the y equals vx for homogeneous and the u equals y1 minus n for Bernoulli, it's about building your confidence. It gives you the tools to look at a scary-looking DE, see through its disguise, and say, aha, I know what you are, and then transform it into something you can handle.
So now you have these new tools in your mathematical detective kit. You're ready to tackle problems that might have seemed impossible before. The only question left is, what kind of mathematical disguise are you going to uncover next?